So what is process simulation? Process simulation is part of process design, but it is not exactly process design. So in outside, you might hear a lot of people saying, oh, process design, process simulation is the same thing. It's actually not the same thing. The importance of process simulation is I want to represent a chemical process by a flow sheet. So a flow sheet is something like this. This is a flow sheet. And this flow sheet shows the major operations in your chemical process. All right, so that's what a flow sheet is. And each flow sheet block consists of a mathematical operation. So for example, in this flow sheet here, let's get my pen up. There is a mixer here, for example, and this is where the feed comes in. So the first is acetic acid, and the second is acetylene. So this is a mathematical operation. Basically, the process simulator does a mass balance to calculate the stream after the mixing, which is called S1 in this one, in this screenshot. And then next, it goes into a heater. So there is also a mathematical operation here, which is Q equals to mc delta P, which is a heat transfer equation. In order to calculate the heat required, so you need some kind of heat input at the site, and also to calculate the outside temperature. And then in the reactor, you also have a mathematical operation where we convert some part of the feed into the product, and there might also be a heat change because of the heat of reaction. Same thing with the cooler, same thing with the separator, which is also a mass balance. So you can see that there's a mass balance recycle, and then there is a product stream. So basically, to put it very simply, a process simulation simply represents a process in a series of mathematical operations. So these are the mathematical operations. We have mass balance here. We have heat transfer. We have reaction engineering. Just put RE. We have heat transfer. And we have separation. And the reason why I asked you guys about your favorite chemical engineering subjects is that you will need the theory or at least a knowledge of each operation in order to actually simulate something so that you understand what you're doing. All right. So let's go back here. And we have covered the first 3 points. The next is steady state versus dynamic simulations exist. So this is a more advanced concept. But the simple way to put it is that whatever we are doing is called steady state. Whatever we are doing now in this workshop is called steady state, where we have some input, we want an output. That's it. All right. However, there's also a more advanced kind of simulation called dynamic simulation. For example, I want to track a unit operation when I start up the plant. So temperature rises. I want to see how the product changes when the temperature rises in a reactor, for example. You can do that, but it is much more time consuming and it also needs more inputs to process. So today we are also going to focus on steady state. So don't think too much yet about the dynamic simulations. So from a process simulation, we can get mass balance, which is the most basic concept of chemical engineering. We can have energy balance. It's the second most basic concept of chemical engineering. We can have equipment sizing, which is needed to actually buy the equipment to install in the plant itself. You can get power and utility consumption, which is required to get the operating costs of some plant that I want to build. And finally, the costing. So the equipment sizing, which will be the capital costs. And then the operating costs will also be factored in to get the overall cost of the project. And then we can know that whether this plant is worth it to build or not. So maybe it's not worth it, then maybe we look for a different process to build. So this is an example of a flow sheet. And this example is, I would say, quite simplified because it doesn't have the actual intricacies of the process. So for example, this vinyl acetate production process can be expanded to a more detailed process. So for example, we have this recycle loop. The recycle loop goes back into the feed here. And we also have, so like in this previous flow sheet, we only represent it as a mixer. It's not that simple. right? After that, we have a heater. So maybe due to some considerations, we cannot just have one heater. We need to have multiple heaters. So in this case, you can see that they are actually a series of 3 heaters. And then there's some heat recovery, heat integration to save energy. All right. And then we have the reactor. And then because that reactor maybe it's an exothermic reaction, it creates heat. So we have like 2 coolers. So again, there's some heat recovery here. So maybe the feed is preheated before it actually enters the reactor. So that's very common in the real process. And then we have the separator. And maybe because this separator is, one separator is not enough to produce the required separation. So we have 2 separators. And this separator perhaps need a lower temperature. So we have a cooling between the separators. And then we have the 2 distillation columns to produce the required product. So a real process does have a lot of intricacies, but usually what you do, the easy way, is to start with this, and then slowly add in the required unit operations one by one. So start with a simple one. Make sure you can get the results. Make sure that you look at the product is correct, the waste is correct, before you go into the details. Don't try to start with the detail. It will get very confusing. Right? So that's how usually we go about doing a process simulation. So you might have heard also about the term called process synthesis. And then you're wondering, why so many terms in process simulation? The fact is that process simulation is, I want to know what this process produces when I already have the process. I have a process, but I don't know what it can produce. So I put this whole process into the simulator. I see what is the output. That is a process simulation. Process synthesis is usually what you do in your design project or your final year project. What you do is, I have a product. I need to think how to produce that product. That is called a process synthesis. So you might be thinking, if that's the case, right, am I joining the wrong class? Because what I'm doing seems to be process synthesis and not simulation, right? Because I have a product I want to produce and I want to think of how to do it. In real life, process synthesis and simulation, they work hand in hand. So first, I will start with some product. Okay, I know I want to produce product X. I think of how to produce that product. I sketch out maybe on a piece of paper about what reactor I need, what heat exchanger I need, what distillation column I need. And then I put that into HYSYS, which is the simulation part. And then I look at the result. Is the result what I want? If yes, then it ends. Okay, that is my final simulation flow sheet. Then I can use it, submit to my lecturer, or I can continue the steps. But usually what happens is that we cannot get the result we want. So we go back to the simulation and we change some parameters. Then we check again. If still doesn't match the result we want, go back to the simulation, check the parameters again. So this process repeats. However, if I iterate quite a few times, I still cannot get the result I want. Maybe there's something wrong at the start. Maybe I have put in the wrong unit operation. This is supposed to be a stripping column, but I have simulated it as a distillation column. It cannot be done. So I will then go back to the synthesis phase. And then go through the simulation process again, check the results, iterate with the simulation, and so on, until you get the flow sheet which produces the result you want. So that's how process synthesis works with simulation. And that's why even though you are doing a design project, you need to do simulation.